Yeah, interpreter performance. As Morten has stated this morning, the Dyalog team has been implemented lots of features in the last 25 years, and we are now in a moment where we can focus a significant part of our work time on improving performance. So there are, if that will work, no. There are several projects going on, mainly in two categories. The first one is multitasking. Morten has talked about that this morning. And the second one is optimizing primitives. Primitives are the atomic parts of the language, right? Functions and operators. So this is where I am working. This is my area. Currently, the projects we're working on are search functions. I think I've already mentioned them last year, and some work is already in 12.0, but we will probably do more work in a close future. Boolean operation was what Roger Huis has been showing to you in the last presentation. Indexing is one of the projects which is partly done, and I will focus on it to give you an example of what optimization can be. Grading, inner product, and transpose are candidates for future optimizations because we found out that we could do significant improvements on them. So, and more to come depending on whatever the users think is important to optimize, and obviously if we can do it. Yeah. So the problems with optimizing primitives, apart from the technical one, I can handle the technical problems with John Scholl's help, but the other problems is that, first of all, any feature, you can work on it forever and try to optimize it forever. So it's an endless job. We have to choose what to do. And the second thing is that the real gain for the end user is depending on what the user does with the interpreter. So we implementers cannot really know what is important to you. So that's why we have created a little tool so that the user can easily send us information about how they use the interpreter and what is really worth optimizing for them. And this tool is APL Monitor. What it is so as written here, primitive level monitor. That means it measures how primitives are used and how much time is spent running them, but without knowing anything about the application itself. It's really an implementer tool. It's not like Quad Monitor or CMPX, which is I don't know if you know it. It's a function in the defense workspace, which is very handy to measure time taken to execute APL expressions. So these are the APL user tools. When you develop an application, you would use them to see where the time is spent in your application. But we will use another tool, which is APLmon, which will tell us which primitives are used the most and which part of the interpreter we could optimize. It's already available in DSS. I think it's been the first batch that had it was in October. I'm not sure. It's still experimental though, so it might change. It has changed lots of times since we started it, and the specifications might change again in the future. The conference edition of the interpreter has it on your USB key. Unfortunately, there's a little bug. So I'm going to, for those who are interested, I'm going to give you a USB key that has a fixed version, so you can copy it if you're interested in it. So the main idea is that you run an interpreter, you enable the monitor at startup with a little command line option, and so you run whatever you want to run in. You use your interpreter as you would use it otherwise, and when you turn it off, it outputs a log file with what has been used. And obviously, if you don't use it, if you don't enable it, it will be completely invisible. It won't change anything in the interpreter. Oh, demonstration. So, I'm not sure how far I should go in showing APL mount, because really, we are going to use it. You will just seamlessly just call it and send us the log. But I'm just to give you a little insight about what it's doing. Also because it might be useful to the user in some cases. So the first thing to do is to create a shortcut to your Dyalog executable and add this -dm option. All of this is in a PDF that is on the USB key, so you don't need to take notes or whatever. It's on the document. And then you specify the folder, which is the working directory, in which the log file will end up. Yeah. And then when you run it, it is so it's an interpreter that is logging everything that's happening. So I can load, for example, a workspace. So I've written my own benchmark workspace, which is very small because I don't have much to benchmark. Benchmark. So here's a little function that is calling. So is it readable? No. But I have no session file. Yeah. How do I do it? Yeah, that's a bit stupid, but okay. Yeah, you believe it. Just trust me. So I've run that function. It's done what it had to do. I turn it off, and a log file should appear on the desktop. Yeah, yeah. So it's a very simple text file in a standard format called CSV, which is where it's basically a two-dimensional table where values are separated by commas. So it gives me the list of primitives that has been used. And so if I edit the function again, nope. So it's basically showing what this function has been calling, how many times each function has been called, with what kind of arguments. Are they integer, are they character, nested, whatever. So we have all kinds of information about how the application has used the primitives. So what we'll do is use a little tool to show the big time consumer. So Morten has written, based on Adrian's workspace that he demonstrated yesterday, he wrote a little functions to explore this data. I'll just show you. So no. So I load a CSV file. Yeah, for example, Konak. So this is the benchmark that Konak sent us. And so we can very easily see, so they are sorted by time usage. We can very easily see where the time is spent. And if we were, for example, to say maybe we could do some special cases in simple indexing, we can also see, we can see what types has been used with simple indexing. So maybe we could do some special cases that are worth optimizing. So that's how we'll use it. For the APL programmer, it might be useful if you want to check what your application is doing. For example, if you have an application that does mainly arithmetics, you would like to check that it doesn't spend all this time reshaping data or whatever. So you can check that it's behaving sensibly. But it's mainly for the implementer, for us. So it would be really nice if all the Dyalog users could make some benchmark, run them, and send us logs, and we will analyze them all and and focus on the important primitives to optimize. So, sorry? You can try, yeah. Yeah, yeah. No, actually, no. It's true that we are not working only on raw data. We would appreciate if there was some comments about which primitives are really important, because maybe you don't care about the most. Maybe the biggest time consumer is not the most important function to optimize also. So, any insight you can give on the files is more useful than trying to cheat on the data, obviously. Yeah. 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 So that was about APL monitor. Now I'm going to focus on an optimization I've recently worked on, and I think it's an optimization that people have been asking for a very long time. So it's on its way. It's half done. I've only done the simple indexing case. I now have to do the symmetrical case, which is indexed assignment, but it should be similar. So how it used to be is if you wrote these two APL statements, then the interpreter would end up with 3 arrays, the matrix you want to index and the subscripts, so 2 subscripts in that case. And what it used to do was to create an array of all the offsets of the result. Okay, so it could fetch all the data from the matrix with this structure. The reason to create this structure, I think, is that it's a consistent way for all indexing operation in the global sense, not just simple indexing, but also for all other kinds of indexing, like rich indexing, choose indexing, but also for indexed assignment, selective assignment, and so on. So this way of working is a general approach that works very well. But obviously, we could avoid generating this array when it's big. It really hits the performance. So what we've done instead, and which is quite sensible, is rather than converting into the whole bunch of indices, just convert the subscript and keep them as subscript, and then loop on this subscript to fetch the data. So in theory, it's about the same amount of operations, but we save memory. And also, we can do further optimizations because we haven't spent time creating the results. We can, without having spent time creating the intermediate array, we can look at the subscript and say, maybe I can do something clever. One very easy case to optimize is when, for example, one of the subscripts is empty. Because what it used to do in that case was to create a whole array, which is unfortunately useless in that case. So we can avoid doing that and save a lot of time and a lot of space by doing this and obtaining the same result. So that's the main idea in indexing. Yep. Yeah. 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 so yeah, so these are the obvious examples, but using that new technique, we can also make all sorts of further optimizations. To sum up, this is not very useful, but it's just, yeah. Another optimization we could do is, for example, when the last subscripts are empty, we can copy blocks of data at a time rather than item by item. And this is especially fast for Booleans, which are 1-bit data, and it's very expensive to move 1 bit at a time. It's much faster to move blocks of bits at a time. There are other optimizations, but then it gets difficult to. The problem when you arrive at a certain level of optimization is guessing, is it worth trying to guess whether it, sorry, I'm mixed up. It's taking the decision about whether you want to special case or not might begin to become more expensive than just doing it. So I'm not going to enter the details of these. So demonstration. I'm going to, oops, that was not meant to be shown. So I'm going to run the V12 as it is at the moment. Yeah? And the new V12 with indexing optimized. And we'll have a quick look at the numbers just to feed my ego. Okay. So one thing about performance measurement, because we are going to measure time, is it's it's interesting to give when you want to measure time in the interpreter, it's a good idea to give it a slightly higher priority, so that it's not interrupted by other user processes. So with the task manager, I can select my dialog processes and say I want a slightly higher priority. Yes. And this one too. Yes. Okay. Because it doesn't make it doesn't make much difference as long as you have a higher priority than the other user processes. Because anyway, the operating system will have higher priority than you, and it prevents it from completely hanging your system if you do something wrong. If you start a computation that will take hours, you can't stop it. So I'm going to copy two very useful functions. I don't know if you know about them from the defense. Oh, it's not. Is it readable? No, probably. Is it a bit? Yeah, that's better. So this function, CMPX, so they are both in the defense workspace. This function is a very clever function that will time an APL expression and will repeat it until it has measured a full second at least, so that the accuracy gets better. Because if you measure a very small time, the granularity of the measurement makes it completely irrelevant. But if you do lots of measurements, the average of the measurements is very close to the real measurements. And it is doing another clever trick, which is removing the time of executing an empty expression, so that it's really close to reality. And WSREC is a function that will tell you how much memory was necessary to the execution of an expression. So I create a Boolean array, and vector of indices. Okay. I'm going to measure a simple indexing. So this is going to take, so this is the expression, this is the time it takes, and we don't really care about the other one. This is when you compare several expressions. You give several expressions to CMPX, it will compare them and will tell you which one is faster. Here we just measure time, so we don't need it. So it's taking 1.4 seconds. That's in the new interpreter, and that's very good, because in the old interpreter, it used to take, it used to be impossible. So I think it's a good improvement in terms of time. Okay? So let's do something that used to be possible. Phew. Faster. Yeah. So in the general case, it should not be slower. There's no reason for the new algorithm to be slower. So it will just, in the general case, it will just save the time of creating the temporary array. So in most cases, it's a bit faster. And obviously, the memory it needs is much smaller. If it succeeds. So the size, bool array, here the size of the result is the same as the size of bool array. So the memory it needs is very close to the size of the result. The difference is just the size of these subscripts, because it has to convert them and check them. So whereas previously it used to take, I think, much more than that. I'm showing you here, I'm showing you the worst case because, so it used to need 33 times the size of the array. This is the worst case. I'm showing you just to be proud of me, but this is the worst case because we are generating an array of indices that has the same size of the result, but take 32 times the size, because the result is Boolean and the indices are 32-bit integers. So this is very impressive, obviously. Okay. Yeah. Anyway, I'm finished. I don't have much to say about it. I think you got the idea. This is a case where there's no memory improvement because we're just dealing with a vector of indices. So we have to convert and check the range anyway. So this is not this. Hey, it's still a bit faster. Oops. Oh. And we'll see that the memory usage is about the same. Yeah. So even in the case that are not the best cases, it's still a little bit faster because of the optimized routines to loop. I'm just going to show you the worst case. This is because I wrote the algorithm, so I know exactly which is the worst thing that can happen to the algorithm. And currently, it's a bit slower, but I will fix it because I don't want anything to be slower than it used to be. So this is very bad because in my new algorithm, I will be looping through all the subscripts twice as more as it used to do. So yeah, I think so. So it's about twice as slow, but I mean, yeah, this is in the general case it will be faster. And just to finish, I'll show you the best case. Well, not exactly the best case, but one of the best cases. So, oh, sorry. Yeah. So the best case is when the subscripts are implicit here. So I I save lots and lots of memory and computations. So it used to take 12 milliseconds, and now it takes, hey, it nearly takes 100th of the time. I think that's quite good. No? So that's the best case. It's just to show off a bit. But anyway, I think that's it. So the conclusion. This was just to show you what we do with optimizations, but the conclusion is down there. I don't really need to show you that. So yes, so the conclusion is simply send us as many logs as you can, even different applications if you have, and we will try to do our best with that. Thank you.